Okay, welcome to a new chapter. This is going to be on thermodynamics, physics style, and this topic is going to include work energy ideas and energy interchanges in actual processes, like the internal combustion engine, gas, work, all kinds of things like that. So we're going to look today at what is the zeroth law of thermodynamics, what's thermal expansion, what are temperature scales, absolute zero scale, and things like that, just to get us warmed up, as I should say. So let's go ahead and get started. Temperature and the zeroth law of thermodynamics. The zeroth law of thermodynamics deals with heat transfer and thermal equilibrium. Something's in thermal equilibrium, that's a fancy way of saying they're at the same temperature. So let's take a look. Our left object here is a warmer object, and the right object is cooler. So heat is going to transfer, between the two of them until they are the same temperature. So the zeroth law of thermodynamics dictates that that will happen. So let's get a difference between temperature right away and heat. Heat, is going to be a transfer of energy. Whereas temperature is a measure of the average kinetic energy that something has. So what's our difference? Well, we're so used to saying, well, it's hot outside, therefore we have a heat wave. Well, that may not necessarily be true. If everything's hot in the same temperature, then no energy is going to be transferring between the two. So heat really is an energy transfer. And yes, that's going to be measured in joules. Whereas temperature is a measure of the average kinetic energy. So if it's summertime and everything's hot, that just means molecules and atoms are moving around much faster. But if everything's the same temperature as in being hot, then there really is no heat wave, because heat would be the transfer of energy. So if it's summertime and I take a big block of ice and throw it out in the street, now we've got a heat wave. Why? Because we have heat outside transferring from the warm temperature area into the cold temperature area of the ice. So hopefully that differentiation there helps us out. So what else does the zeroth law of thermodynamics tell us? Well, let's call this object A here and this object B here. And our thermometer is going to be object C in both cases. So let's say I've got some metal here, and I take a thermometer and I place it on there and I measure its temperature, and it looks like it's 60 degrees Celsius. So we now know that the thermometer is in thermal equilibrium, with the metal. Why? Well, heat will transfer back and forth until both of them are the same temperature, in this case measured by our thermometer. And let's say I've got a sample of metal B over here, and I take the same thermometer and move it over there, and it reaches thermal equilibrium, meaning the temperature of the thermometer is the same as the metal, and we measure it to be 60 degrees Celsius. So since object C is in thermal equilibrium with object A, and object C is in thermal equilibrium with object B, object A and object B also have to be in thermal equilibrium with each other. So what this means is all objects that are at the same temperature are in thermal equilibrium with each other. So it's kind of logical. And then you might be wondering, so is there error in measuring temperature? The answer would be yes, because when you put the thermometer next to something, energy is going to have to transfer, whether from the thermometer to the material or vice versa, until they are the same temperature. So a little bit of heat flow has to occur between there. So just like we had in circuits, the ability to measure something means you have to disturb it to get its measurement. So there's always some error in making measurements with temperature. So hopefully that helps you understand our zeroth law of thermodynamics. Pretty basic. The idea that objects at the same temperature are in thermal equilibrium with each other. And if they're not in thermal equilibrium with each other, heat will flow from the warmer object to the cooler object until they are at equilibrium. And what we mean by that is the same temperature. What about temperature scales? Well, water is a very common substance. And here we have a block of ice, and here we have liquid water. Okay, and of course we can actually boil the water. So this is where it's solid, and then liquid. And of course I don't have a picture of a gas because there'll be a vapor there, so we'll just do a letter G here. Okay, for gas. So what's our temperature scale in degrees Celsius? Well, basically it's a degraded scale. That's why we call it degrees. What we've done is we've taken water at ice to be 0 degrees Celsius. Okay, and basically it's in thermal reversible process. Okay, at 0 degrees it will melt and freeze, okay, back and forth in equilibrium, okay, at 0 degrees Celsius, back and forth, back and forth. So what that means is the amount of water melting is equal to the amount of water freezing. So that process we've labeled 0 degrees Celsius. Okay, now what about when it begins to boil? Well, we just simply call that 100 degrees Celsius. Okay, now what does boiling mean? Well, boiling means when we're at the equilibrium point where the amount of liquid becoming a gas is equal to the amount of gas becoming a liquid. So it's another equilibrium point. We call that the boiling point of the liquid. So for Celsius, we call ice, okay, 0 degrees Celsius when it's at the melting point or freezing point of it. And when we're at the boiling point of water, we call that 100 degrees. And what do we do? We simply break that down into 100 pieces in between. So that's where Celsius comes from. So 0 degrees Celsius is when we basically have the freezing point of water. And 100 degrees is when we have the boiling point. Okay, what about degrees Fahrenheit? Well, we simply call this one 32 degrees Fahrenheit. Okay, and this is going to be 212, okay, degrees Fahrenheit. Okay, so both of those are called degraded scales, okay, and that's because we establish one temperature and another temperature and then simply break it into pieces, 1 degree in between each, and likewise with our Fahrenheit scale. Okay, what about another scale called the Kelvin scale? Well, this one is not a degraded scale. Okay, so we're going to talk about the gas thermometer now to help you understand. Okay, Kelvin, named after Lord Kelvin, made a relationship between molecular motion and temperature. So let's take a look at our device here. This is called a gas thermometer. So what you have is a sample of gas, and you can place it in a beaker of water at a certain temperature. What's going to happen is you're going to have gas molecules bouncing around all over the place and creating a pressure here. That pressure is going to push on a liquid. Now, typically mercury is used in this. So what it does is it pushes, okay, the mercury up, and we'll talk more about how we measure pressure later. But basically, the amount of mercury above this level is going to be related to the pressure, okay, in this gas here. So if I warm this water around the outside of it, I will warm the gas inside, causing the molecules to bounce around more, creating greater pressure, and that's going to push this up more in this direction. If I cool it, this is going to go back downwards, and there'll be less mercury above this level because the gas molecules are not moving as quickly. Okay, so if we take a measurement here of pressure versus temperature, regardless of what gas we pick, so we can, do a variety of temperatures, a variety of pressures, and make measurements using this device. And then what we notice is there's a linear curve. So as temperature decreases, so does the pressure. Well, at some point, you can just simply, stop taking data with a straight line, and then you can extrapolate all the way to the x-axis. Okay, for each of the gases, no matter what you do, you get an extrapolation to minus 273.15 okay, degrees Celsius. Okay, and we're going to call that then absolute zero. Now this again is not a degraded scale because it's based on actual pressure or molecular motion. Okay, so when you have 0 Kelvin, you cannot go below that. Why? Because all molecular motion is believed to cease at 0 Kelvin. Now remember, this is only a theoretical construct. There's no way to completely isolate any material totally from any source of energy, stopping all motion inside. So 0 Kelvin is then equated to minus 273.15 degrees Celsius. So Kelvin then is equal to basically 273.15 plus your degrees Celsius. That's where we get the conversion for that scale. But again, the concept is absolute zero. You cannot go any lower, okay, in temperature than that. And it's not a degraded scale because it's not based on a beginning and a final and breaking up into pieces. It's based on actual gas pressures. Okay, and our final topic for the introduction in thermodynamics is thermal expansion. And the basic gist of this is as you warm something, atoms begin to vibrate faster or move faster, and the length of the object changes. And vice versa, of course, if you cool something, the length will actually get a lot smaller. So the equation for a linear expansion goes like this. The change in length of an object is equal to alpha, which is a linear coefficient of expansion, multiplied by the original length, okay, times change in temperature. So alpha, you can get into a table there. Okay, let's say if this is a piece of aluminum here. Aluminum will have a certain alpha value. Now we'll have a beginning length of this. Let's just call this side L and just do double arrows here. So let's say we know the length of our object here. So we would plug our length in here, and then our alpha coefficient, you look up in a table, and then what's your beginning temperature and final temperature. And that's going to equal to the change in length, okay, of our object. So that's linear expansion. So it's pretty easy. You just plug and chug, and these coefficients just come from, you know, taking an object and measuring its length and then changing temperature and then doing a line of best fit. Okay. Now what about the change in area equation? Change in area equation is this Greek letter gamma multiplied by beginning area multiplied by change in temperature. So what if I wanted to know the change in area of one side of this? Well, I can just go my length, and then of course this would be times my height this time to get this area. I would plug that in right there, change in temperature. Okay, now gamma, Greek letter gamma, is going to equal 2 times alpha. Let's draw that alpha a little better there. Okay, that's supposed to be an alpha symbol. Why is it 2 times it? Because you have this that's going to change in length, and this side here is going to change in length. So that's going to be 2. I might try to draw alpha again. There we go. Okay. Okay, now what about the change in volume? Well, change in volume is going to be beta times beginning volume times the change in temperature. Okay, now we'll have basically a length, okay, height, and then of course a width. We can calculate the volume of this. So how does the volume of this thing expand? Well, you'll have a beta, okay, which is your volume expansion coefficient multiplied by original volume times change in temperature. Okay, now what's beta equal to? Well, beta is going to equal 3 times alpha. Why 3? Because you have this changing in length, this one changing in length, and that changing in length. So thermal expansion is pretty easy. Just, you know, put numbers into the equation and then solve for the change. Now if I want the final length of this, I would take the change in length that I just calculated and then add it to my length. So that's the introduction to thermal. Of course, we'll get into more detail soon.